Good afternoon. As the room is well filled, I think we can slowly start. My name is Untitled from University. I will chair this afternoon sessions. And our first speaker is Morozov from Edinburgh University, and he will speak about stochastic kinetic theory of dilute microswimmer suspensions.
All right. Thanks very much. First of all, thanks very much to the organizer for their very kind invitation. It's a pleasure to be here. So what I will talk about today is highly experimental in the sense I've never talked about this before, but I really wanted to present it in this audience. It's a very fine line between giving too many and too few details. You will see in a second what I mean. If I'm losing you, please stop me at any point. This will be important. So before we start, I want to acknowledge that support from EPSRC. All the simulations that I'm going to show were done in Archer 2 and supported by the UK Turbulence Consortium. So this is the work largely of Victor Shkulteti, who was a PhD student with us. Now he's in EPFL, and done together with the long-term collaborators of mine, Cesare Nardini and Joachim Steinhammer, and both in the audience, and talking here later, and Davide Merinduzza from Edinburgh. All simulations were done with Daedalus. I'm not going to present technical details, but please ask me later on if you're interested. I'm a big fan, and we've been given a lot of support by their team. We even hired one of them recently in Edinburgh. It's very useful if you want to get into simulations of large scale, either flows or active models without worrying too much about numerical details. Before we start, I want to continue from where Ulrike stopped. This morning, University of Edinburgh is a university of sanctuary. We've recently created about 40 studentships for all PhD students displaced by various conflicts around the world. If you know anyone who might profit from our help, please let me know. In a similar fashion, I'm a part of the program run here at the Isaac Newton Institute, who are supporting displaced scientists in mathematical sciences, where mathematical science is being understood very, very broadly. Yet again, if you know someone who would profit from our help, please let me know. Right, so my fascination personal in active matter stems from the following. Really, compared to equilibrium.mag, individual agents can self-propel, exert forces and torques on the surroundings, and often in this process they break detailed balance on the microscopic level. That means that the system can now exhibit macroscopic currents, so suddenly your tea can stir itself without any energy input from the outside, and this often leads to what people call collective flows or collective motion, bacterial turbulence, active turbulence, and this is kind of the main topic of interest. These are just two examples. I think some of you have seen them at nausea. One of them is bacterial turbulence, where you have a collection of individual motile cells, which are smaller than a dot here on this picture, and you see large-scale vortices flying through the system. The other is an extract from cells, where you take the macroscopic collection of small filaments and molecular motors in the presence of a depletant agent, and you again start seeing these large-scale flows. So mathematical understanding of this type of flows is something that we're after. This already been discussed a bit by Julia this morning. So what I will have in mind, although I will not need this at all, but this is just kind of an example of a physical system that I want to keep at the back of my mind, are bacterial suspensions. In this particular case, it's E. coli that does the classical run and tumble. So it's a micron-sized object that runs for roughly a second at the speed of between 10 to 30 micrometers per second, depending on the specific strain. And then with the frequency of roughly once a second, it randomly changes direction. As a matter of fact, these reorientations are not entirely random. To a very good approximation, you can just say that it stops on the spot, chooses the next direction, and starts going there. All of this is happening at such scale that the Reynolds number are minute, and so from all perspectives, this is Stochian, and you might imagine this is boring, and yet you start seeing these large-scale collective flows, which are not inertial in origin. Again, showing the same picture, just to show that in dilute suspensions, the long-range interactions between bacteria are stemming from the dipolar fields. And so this is a seminal paper from Ray Goldstein's group, where they actually measured the velocity field far away from bacterium. And what you can see quite convincingly is that at scales larger than the, say, size of the organism, the velocity field is well described by dipolar field. So, as Julie already introduced, these can be, depending on the symmetry, well, not the symmetry of the field, but the direction of the field, can be quantified as pushers and pullers. Pushers are typically bacteria that ejects flow from the tail and the head. People often say that clammy are pullers. This is not entirely true. Jerry Golub's lab have very careful studies of this, and algae actually oscillate between being puller and pusher. On average, they're slightly more puller, and therefore this is kind of often viewed as the second type of the singularities. Okay, so before we go to
a question,
yeah.
Are there well-studied organisms that have no significant force dipole and are really like those things those chloride that crawl along their surface that you see in Purcell's article or someplace? I mean, there's
so it's a complicated question that I'm sure many people in the audience know a better answer to. So some amoeba have metachronal waves running on the surface that are neither pure pushers or pullers, but have high order moments. I've recently came across a wonderful organism which it looks like a flying saucer with a tail that connects to its head and turns around, creating a green vortex or tailor vortex, and hence propelling itself. So there is a variety of very different propulsion mechanisms than just these, but this is taken for simplicity. Okay, so I mean, there is a lot of interest in this collective motion, but what I wanted to stress is that way before any collective motion can be observed in bacterial suspensions, there are very different situations at very low dilution where you see mechanical properties which are very, very different from normal fluids. And so one of the examples is the classical enhanced diffusivity. So you put a tracer in a bath of a very dilute suspension of bacteria such that bacteria are very, very far away from each other. You look at the motion of the tracer, and if you're only interested in the second moment, this is diffusive for all practical purposes. However, the diffusion coefficient can be up to 100 times larger than thermal diffusivity, and this comes really from the fact that bacteria stir the fluid. You sit in your bathtub, you move your hand, your favorite rubber duck moves around, and this is the effect. Okay, this can be quantified, and many people looked at this, so notably Jean-Luc Tifo, but also us and Julia Yeomans's group. And essentially at very low dilutions, you can think of this as individual scattering events, how a tracer is moved by a swimmer moving far away, and you can actually sum this up independently and end up with a number which is very, very close to experimentally measured value. Another kind of interesting result, which happens way before collective motion sets in, is another mechanical property, which is the viscosity, and that's another thing that kind of signifies that when you break detail balance at microscopic scale, anything could happen. This is from the group of Eric Clément, and we worked with them later to kind of clean this up a bit. So the main observation is you put bacteria at very, very low dilutions in the rheometer, you measure the viscosity. As a matter of fact, the viscosity goes down as the bacterial concentration. So what you see here is the ratio of the viscosity of the apparent viscosity of the solution to the suspending fluid. And you see as a matter of bacterial concentration, roughly about 1%, it goes through zero as far as we can tell. And so this was mentioned as bacterial turbulence, as bacterial superfluidity. I'm not entirely sure about this, but the mechanism for this is quite simple. Ask me if you're interested. So kind of the phenomenology of this can be summarized as following. If you're looking at dipolar bacteria at very, very low volume fractions, so typically up to 1%. So this is not representative of a picture. So typically at 1%, the typical distance between bacteria is more than 10 micrometers. So they're well separated. Then below, you do not have a trivial fluid. It's a fluid with very fine mechanical properties. And when you cross this boundary, you start seeing these vortices and jets, which are represented on the right-hand side. So the way one typically deals with appearance of such collective motion is really kind of a series of works from various groups. The original contribution, I believe, in this particular setting was David Santian and Mike Shelley, who introduced a description in terms of the kinetic theory. So you are looking at a mean field theory in terms of a probability distribution function to find a bacterium at some position with some orientation. So this is a direction in which it swims. Its microscopic dynamics is simple. It's moving because it swims in the direction of its orientation. It's being moved around by the fluid, and it's being turned around. So this is the update for the orientation, the Jeffreys equation, where essentially you are saying that depending on the strain and the vorticity of the fluid, you would be orienting if you're an elongated object. So parameter B controls whether you are elongated an object, which is 1, or B 0 being a sphere. So you would turn around in the fluid. Final element of these dynamics, which are very, very difficult to write as PDEs, but very easy to write in terms of kinetic theory, is tumbling. So the right-hand side describes leaving a particular point in phase space with some rate lambda, which is the tumble rate, and coming back to that point in phase space from all other points in phase space by tumbling yet again. The velocity field is at the point where a microorganism finds itself is really just a superposition of the velocity fields created by all other organisms at this point, which are taken to be just long-range dipolar interactions. This is the classical example in 3D, where kappa, and this will be important, is the dipolar strengths. So this is the typical scale of the velocity field created by a microorganism throughout the volume. So the base state of such suspensions at very, very low dilutions is simple. It's homogeneous and isotropic. And when you do linear stability of this state, it becomes unstable. It's very interesting that the positional or translational degrees of freedom do not participate in a linear stability problem. It's only the orientation that matters. And what appears from that calculation is there is a critical threshold set either in terms of the critical density of the bacteria, but if you are also determined to do this in simulations, you can either choose the tumble rate or the dipolar strengths, above which the system becomes unstable. The dispersion relation is such that this instability is long wavelength, so this means that essentially the whole world wants to become aligned in the first instance. That state, as we know by the famous Sima-Ramaswamy instability, becomes unstable yet again, and this is essentially the origin of persisting collective motion. You can extend this result to any dimension above 1. And this is what we've done because this will be important later on. And exactly the same happens in any dimension where the now onset is given by just a different prefactor where D is the dimensionality of space. Right. Okay. So simulating these equations is, the colors are kind of funny, is quite painful because working with the kinetic theory at the level of the Smolkovsky equation is highly dimensional if you are even in 3D. And so what one usually does is expands the probability distribution functions in terms of moments. The dynamically unstable quantity is the Q tensor or the pneumatic order parameter that Julie introduced this morning. So this is the variable that goes unstable in the first instance. And so what one typically does is is keeping a few moments up to the dynamically relevant one and do something about higher order moments. They're doing something about higher order moments, has several choices. One is you just drop them. This produces a theory which is fine at the linear level. However, if you try simulating it, there are some technical difficulties there. So, for instance, you above a certain density, you start seeing small-scale noise because there is not enough regularization. And so, what we decided to do is our choice is kind of more based on amplitude equations type of thinking, or Ginzburg-Landau, where we keep the first 3 moments, then we enslave the next moment, case 3, and drop all other moments. Okay, so what this does, it doesn't change the phonology of the equations, it just helps with numerics, really. So what you get out of this is a system of equations for the density, which is C, for the polarization on average of the suspension. So you draw a small box somewhere in the fluid, you sum up all the orientations. This is on average the polarization of that volume element. So this is M, and there is the Q tensor here that obeys this horrible equation where the upper and lower convective derivatives are given here. If you've worked with liquid crystals, this is exactly what you get from John Hinch and Gary Leal's 70s paper on coarse graining kinetic theory for liquid crystals. The only difference is that now there is activity. The activity kicks in as the divergence of the Q tensor in the Stokes equation, where, funnily enough, there is a combination of units such that there is only a single parameter entering the theory. So if you scale time on the inverse of the tumble frequency, length, velocity on the swimming speed, length on the persistent length, so how much you swim between 2 different reorientations, and all moments on a nominal density, so this is the average density of my suspension, then the only parameter in these equations really is delta, which is a combination of the elongation parameters, so this aspect ratio, dipolar strength, the density in your suspension, and the tumble rate. And this is the only thing telling you how far you are from the onset.
Sorry, I missed something.
Yeah.
So what is the closure on Q3?
So Q3 is linearized, so it doesn't have its dynamics, so you only keep linear terms, so you algebraically solve for that and plugged it back.
Delta Q3.
Sorry, yeah. All gradients and higher order terms with Q3 you know. Okay, so these now can be simulated, and what you observe is a kind of simple sequence of transitions. In 2D, if you choose to do this in 2D, there is a trivial state where nothing moves, there is no orientation, the concentration is constant. First, you go to a stationary pattern, which has a profile of this is the concentration and the velocity field are small errors. Then next, you go to a periodic orbit where this stopped moving, where essentially this pattern start flopping around periodically. And finally, at higher distance from the onset, you start seeing these movies which you've already probably seen before, which is the concentration field C, or the deviation from unity, and the eigenvalue of the Q tensor, which really gives the feeling of this chaotic patterns on a large scale. The first 2 states, which is a stable pattern and the periodic orbit, are very rarely discussed in the literature because it's very difficult to find them. The reason why it's difficult to find them is the following. So imagine I'm going to simulate a small system, I'm going to, which way this goes? So I'm going to increase my distance from the threshold of the instability by minute amounts, and I'm going to look at the fluctuations of some observable. What you're seeing is that there is a stationary pattern, then there is higher periodic orbits, that become more and more complicated, then they lose stability and become essentially chaotic, which can be seen on the Fourier transforms of the same trajectories. And when we measure the boundaries between those states as the function of the system size, you see that these decay very rapidly to ridiculously small numbers, and these are very, very small systems. And so whenever you're simulating this in a large system, you never see this because it's confined to minute state. And so what you really see in simulations, there is a trivial state where nothing happens and this mean field turbulence. Okay, fine. So this is kind of just to show that we can do it as well. There was lots of discussion recently about spectra of active turbulence. Ricard Dilute and colleagues have made an important contribution cleaning this field up a bit. Essentially in 2D, you can measure the spectra of either kinetic energy, which is not particularly useful because it's a quantity which is enslaved to the Q tensor. And so we looked at the spectra of the Q tensor that have particular power laws that we understand. And interestingly, in my second life, I'm very interested in chaotic flows of polymer solutions. And exactly the same spectra have recently been reported in either homogeneous and isotropic turbulence of dilute polymer solutions, or we've recently shown that in the channel flow, you see spectra of very similar decay laws. So it might be that some details of this spectra are really a property of the upper convective derivative and not of the fluid as such, but to be continued later, I guess. We've also tried to rationalize this a bit by measuring the length scale, and there some very interesting kind of surprises came out. So you can identify a typical length scale from where the spectrum of the Q tensor going from one regime, which is the large scale flows dominated by random dipoles essentially, to small scale dynamics within the patch. You can measure this as the function of the distance from the threshold, and what you get out of this is a length scale which is absurdly large. So this length scale we can measure in 2D and in 3D independently. So what is shown here is the typical length scale in terms of run lengths. So for an E. coli, a typical run length is as 10 micrometers. So if you compare this to kind of a typical experimental sizes of microfluidic devices where people do this experiment, this is significantly larger than anything else that you can get either from the experiment or from the theory. As far as we know, this length scale has nothing to do with any linear instability that I'm aware of. It's kind of very different from the length scale that people measured in active pneumatics or in isotropic liquid crystals. And frankly, we're slightly at a loss how you can extract such a large quantity out of these equations. But this is kind of a tangent at the moment. So this is what you get if you honestly perform simulations of these mean field model equations. And the second part of this talk is that the situation is very, very different, fundamentally different, if you start looking at agent-based simulations. So different that I'm really wondering whether the first part is actually describing anything. So let me get you through this. At least you're awake. Good. So we've done this maybe, what, 5-6 years ago, when we wanted a large-scale simulation with many individual agents that swim through the fluid, tumble around, and interact through long-range hydrodynamic interactions and nothing else. So this is based on that particular paper. The method was developed by Mike Cates and co-authors earlier on, and it's a lattice-Boltzmann technique. So microswimmers are point objects which live sub-lattice. They can turn around and stir the fluid, and they move around sub-lattice while the lattice-Boltzmann method is taking care of the long-range hydrodynamic interactions. This is incredibly efficient and allowed us to simulate up to 1 million microswimmers in large boxes. You will see in a second why I want to go to such length. And the phenomenology, what you see there, is kind of similar if you don't look at the details. So at very low densities of microorganisms, you see a cut through a three-dimensional box where you see these small errors flying around, small vortices. The color tells you that the fluid going out or into the screen. When you go to slightly larger densities of the bacterial bodies, you start seeing this very large-scale collective motion. Compared to the swimming speed, this is essentially noise. This is up to 3 times larger than the individual swimming speed. So from the phenological point of view, this is very, very similar. However, if you start measuring things, that's when first kind of red lights start flashing. Depending on, you can do many things. We decided to do the following order parameter, which is you put your finger somewhere in the domain and you measure the velocity fluctuations. On average, the velocity field is not pointing anywhere because this is random, but you can look at the variance of that quantity normalized by the swimming speed of a bacterium. And you see, first of all, that it's non-zero at any concentration, and this is obvious because a large collection of randomly oriented dipoles is going to stir fluid. And so naively, you would say that this is the central limit theorem, and you expect this to kind of increase as a square root. Unfortunately, deviates from this behavior at any density. If you zoom in, the Poisson line is systematically higher than this. A polar line is systematically lower than that prediction. And then at some point, roughly where the mean field theory would predict an onset of collective motion, there is an increase in this quantity and then a saturation. So when you look at the system here, it looks like bacterial turbulence from all practical purposes. But what is happening here is a very smooth going from one phase to the other without any criticality of sorts, if you wish. Same happens if you look at the spectra, which, by the way, look quite different from the spectra of the mean field model. Right, so in order to make sense of this a bit, we looked at the kinetic theory with correlations. I'll go through this rather quickly because this is just a tangent to what I want to tell you, but it introduces some of the methods. So instead of looking at the one particle correlation function, we'll look at n particle correlation function, which describes the dynamics of the whole system, but there is very little what you can do with this technically. And so in order to process this amount of information, we confine ourselves to 2 correlation functions, f, which is a 1-point object which we used in the kinetic theory in the mean field approximation, plus the 2-point correlation function that encodes the correlation between microswimmers. You can actually solve this exactly, more or less, up to the onset of collective motion. And what comes out of this, oh goodness, is we essentially can predict quantitatively how one would approach the onset of collective motion. However, and we were able to get all the divergences in various quantities as one would approach the onset of collective motion. However, the problem is that all of this is too much based on the previously discussed mean field thinking, and as one actually looks at these curves, there is no way you can identify any of this as critical behavior. So, naively I would say there would be a point where you would be branching very sharply from the previous phase, if this is an instability or a phase transition. Of course, in finite systems, this could be smoothened quite a lot, and we were worried about this, so we went through a series of simulations with yet increasing system size, and this was increased quite a lot. That's why we needed such large simulations. And you probably do not see this, but the last 2 lines are really on top of each other. These are astronomically large simulations, and we don't see any sharpening here. So the same was seen independently by Subramanian and Krishnamurti in their measure of the onset, where they looked at the trace diffusivity and tried to identify where the onset would be. So, for instance, these are the typical curves of the trace diffusivity, and this line indicates where you're going to see an onset, and obviously there is nothing special happening at this point. So, in order to try to rationalize these observations, we decided to go back to our equations and introduce correlations. So in that work, when we looked at the correlations before the onset of collective motion, we saw that in order to describe the system, you can either work at the level of the BBGKY hierarchy, where you're looking at the series of correlation functions higher, excuse me, higher than 1 point correlation function. Or alternatively, which is technically exactly the same, you can work with one particle correlation function plus a carefully selected noise, which would encode all the correlations between microswimmers. So using those methods, we derived a new system of equations which looks exactly like before. So these are mean field equations for the concentration, polarization, and the Q tensor. But now there is a noise term present on the right-hand side for the two higher moments. And these noise correlations come really from random reorientations of the microswimmers. So their noise on their polarization and noise on the Q tensor, they have the same structure where the prefactor is given essentially by the run length divided by C naught. So this is 1 over the number of particles in a small volume given by the run length, if you wish, in 2 dimensions. And the right-hand side contains their density and the Q tensor in a proper tensorial form. So this looks horrible, but as a matter of fact, this is just there in order to ensure that the Q tensor is traceless, nothing else. Again, there is only a single parameter other than that noise prefactor, which is the delta, which I will be using as the distance from the onset of criticality, although what I will be showing in a second, there is no criticality at all.
Given the arrival of the noise, is there any adjustment or renormalization in the transport coefficients in the moment equations?
No, so this is exactly what we're after. This is the vanilla version, and kind of what we are now doing is we're thinking of how to use that noise to renormalize all the properties. Exactly.
So one
Yeah.
question.
Yeah.
The active stress should also be proportional to the local concentration, right?
Yes, that's correct.
Equation.
Yes.
Is your Q tensor is only the Q tensor, or is it a tensor density which includes the concentration?
No, so we never select the concentration out of it. So it's C times Q in.
It's actually it's actually got both.
Yeah. Okay, so now comes the bit where I really need to drag you through this. This is not entirely technical, but that was a very important point for us. So if you look at this Stokes equation, sorry, I just realized this is incredibly annoying. Delta is not a Laplacian. This is not bi-Laplacian. This is my distance from the onset, and so this is divergence, and this is a numerical prefactor. Okay, so this is linear. I can solve this, and I know the velocity field in terms of Q all over the place. Okay, so formally I can interpret this. Q drives U. I can put it back in there and deal with that. There is a catch, and the catch is not every part of Q contributes to U. So only a subset of the Q tensor drives the flow. And you can immediately see that it's a kind of trivial statement, because if there is a part of Q, and by part of Q, I'm not talking about some Cartesian components. I am thinking of separating Q into 2 bits. One is such that its divergence is 0, and therefore it's not going to generate any U. The other bit is something that does project on U. And so this asks for a mechanism of splitting this Q tensor into 2 important bits. And so the way one does it is the observation that if I look at the Fourier transform of the velocity gradient, now I'm doing this in components, And you can derive exactly that this is going to be Q times a projection operator, which is orthogonal to the direction, local direction of the wave number, and another projector, which is the longitudinal one. As a matter of fact, this is a very natural thing to look at if you go back and look at the linear instability of the homogeneous and isotropic state. So imagine I now go back to my mean field equations. I have my homogeneous and isotropic suspension, and I'm going to perturb it with a wavy perturbation oriented in, say, X. When you go through the linear stability analysis, you see that the dynamical quantity that becomes unstable is the component QXY of the Q tensor. So what this means is that if this is the direction of the order, my nematic order wants to be at 45 degrees to this direction at the point of the linear instability. So order in one direction, and the dynamical component which is unstable has one index along the order and one index perpendicular to the order. And so what that object does, it selects one of these indices perpendicular to the local order and one of the indices parallel to the order. So the right quantity which couples to the velocity is not the Q tensor, but this symmetrized combination consisting of one index being selected perpendicular to the order, one parallel to the order, the symmetrized version. As a matter of fact, you can look at this from the purely mechanical point of view, and you will see that this is the local strain rate. Okay, so it has a very simple mechanical interpretation. And so therefore, you can split your Q tensor into two bits. One is what we call curly Q, for the lack of better word, which does couple to the velocity. The other bit is the rest, and that does not have dynamics of its own at the point of linear instability. It's driven by that quantity. Okay? And so when you now start thinking about this in terms of renormalization group type of techniques, then you observe that that is dynamically relevant a quantity. It becomes unstable. Their polarization is truly irrelevant in every sense of the word. Then the density couples that bit to that bit. And so to lowest order, you might want just to look at the dynamics of the curly Q, so the bit that couples to the velocity. And this should be true below the onset of the instability. Above the onset, you might want to keep everything but the polarization, but we decided just to do something different, and I'll talk about this in a second. When you put all of this together, it appears that the upper critical dimension for this model is surprisingly 6. It's very, very different from the usual 4 that you get in various non-equilibrium StatMech models, which also tells you that you're very far from the upper critical dimension if you work in 2D or 3D even. And so this raises many questions on how to address this. Right. So below the transition, as I said, the most important dynamical quantity is my curly Q. And when you project everything on the curly Q, you end up with a very simple equation, which is linear in Q. It has time derivative. It has Laplacian, which comes not from the diffusion, but from the swimming of individual microorganisms. And that is just the distance to the onset. It's driven by the noise that comes from the local tumble events of bacteria that has this horrible form, but this is really just keeping it in the right tensorial subspace of my Q tensor. And this is really just the classical model A. And we know everything about this model, so you can solve this exactly. And when you do, you recover all the results that we got from BBJKY just below the transition. So this is the right description, and the Q tensor, which we call curly Q, the subpart of Q, is the right order parameter. Okay? The next question is, however, what happens if you now forget about what happens below the nominal instability and go to the full-scale nonlinear model? And so these are purely numerical results, and I really slow down because I want to discuss this in detail. So instead of working with those simplified set of equations, we decided to just go and simulate the system in the presence of the noise. The only simplification is that we know that close to the onset, the only relevant bit is the curly Q. So all the noise components that do not project on curly Q are dropped, and what you end up with is a very simple noise that keeps only the nominal density here and there, and all these other terms disappear. So the noise variance becomes significantly simpler. Yeah, perfect. And so what we're going to do now is kind of the two-pronged approach. If I show you the simulations of the actual full model, you will be as surprised as we were when we first saw them. So I will cook this very slowly for you, okay? So I know that below the onset, the nominal onset, I can solve all the correlation functions exactly. And if I look at the time correlation function between the two Q tensors, then this is decaying like this, where the onset is at delta being 4. So this time scale diverges exactly at the nominal mean field transition. It's not entirely exponential because there is this correction, so it's not true a diverging time scale, but it's close to that, and we can measure this. So I know that this is true for a linear system, so I'm going to take my full nonlinear system of equations, multiply all nonlinear terms by a prefactor that is 0 in a linear theory and 1 in a fully blown nonlinear theory, and I'm going to slowly increase it from 0 to 1, thus interpolating between the linear theory that I can solve to fully nonlinear one. And so what we do, we measure curly Q correlation functions with just strain tensors. We fit it at long times to the exponential. We extract a time scale from that fit, and we plot it as the function of delta. So in the absence of nonlinear terms, you should observe this time scale, and this is time scale -1, so it's really this prefactor, to go through 0 at delta being 4. And this is indeed what you see here. It deviates from the straight line far away from the transition, but close to the transition, it just linearly crosses 0. If you now start increasing the strength of my non-linearities, which is measured by this NL, for the lack of better notation, what you start seeing is that divergence very slowly pops up higher and higher. Well, not divergence, this behavior changes to such that it never crosses 0, it never diverges, thus really telling you that there is nothing critical happening at this point and there is no transition. We've checked also, because these are stochastic simulations, it's very, very difficult to get them to, well, not difficult, it's very difficult to understand what convergence in this sense means. So we've looked at how these curves behave if you increase the system size, and this is done here at various purple curves. They keep changing as you change the system size, but importantly, as you increase the system size, they go higher and higher up, away from crossing this boundary, really telling you that in the thermodynamic limit, I'm going to be very far away from any type of criticality. Right, second game you want to play, which is now something completely different. I take my full nonlinear system of equations and I switch off the noise. What I'm going to observe is the active turbulence that I've seen before. Okay, I can measure my variance of the curly Q. What I'm going to see, because this is log scale, I'm not plotting this because it's impossible to plot here, but there would be nothing and a kind of square rootish type of onset of something at delta being 4, which is the critical point in 2D. What I now do, I multiply the noise by another interpolating variable, and I slowly turn it up from 0 to 1. And what you are seeing is that suddenly there is something non-trivial below, at any density below the onset. It's kind of sharpish for very small prefactor. As I turn it up to 1, which is what it should be, you lose completely any sign of criticality in this model. Finally, if I do this on a very different level, I mean, until now I've just been talking about how these things behave in some measured quantities, but let me give you the visual indication of what is going on in the system. So here I'm plotting the eigenvalue of the Q tensor as the function of the distance to the onset, and again, 4 is the nominal mean field transition. And this is the strength of my noise going to 1, which is really what it should be. Here is the kind of classical active turbulence. I was about too clever with colors. I apologize for that. So you see these domains and large-scale vortices. As you increase the noise strength, these domains become smaller and smaller. And finally, you just lose all of this, and you just see small-scale noise. And so all of this put together points to the following. When I'm looking at the transition to collective motion in 2D, I have two choices. Either there are correlations, or in terms of what we've done, there is noise, or there isn't. And there are these two types of theories which are very, very different in their phenomenology. At the mean field level, there is an instability for pushers. There is no instability for pullers. There is a transition, it's kind of isotropic pneumatic transition plus the Ramaswamy. So this is the mechanism how these active flows are sustained. There is a length scale which is selected by a strongly non-linear mechanism that we do not quite understand. The emergent length scale is very, very large, so we do not quite know where this comes from. However, when you start including correlations, all of this falls apart. While the mean field theory predicts nothing below the onset and then active flows, in actual simulations of microswimmers, you always see a lot of correlations before the onset that become stronger through the onset. Swimming somewhat suppresses correlation. I didn't have time to talk about this, but this is what came out of our kinetic theory. However, the new bit is this. We do not see any transition to collective motion in a 2D model. The upper critical dimension is 6. There are some indications that the low critical dimension can be renormalized away from 2 to something higher, and probably there is no onset of collective motion and in two-dimensional systems, and active turbulence in agents can only be studied in systems of higher dimensionality. Does this mean that noise induces a crossover more than a transition? How does one think about this being one phase throughout, even though you see vortices of different sizes? All of this are kind of very interesting questions. Last thing I want to point out before I stop is that exactly the same power counting applies for systems with rotational diffusion, so you do not need to have tumbling to have all of this, and to isotropic active liquid crystals, so active gels taken below the point of the isotropic pneumatic transition. In the presence of noise, all of them do the same thing, which is kind of wiping out any sign of collective motion. I stop here. Thank you very much. I take questions.
Me? No, I didn't understand your statement about the upper critical dimension. What nonlinearity becomes relevant below 6 dimensions, and I just completely missed that bit. Could you please?
Well, you didn't miss this. I didn't talk about that.
Good. Then I feel even better.
Yeah. So the important bit, the one that really drives the instability, is that coupling.
Right. Yes.
Okay.
So what's the argument that for 6 dimensions being the place where something happens? I just missed that.
The argument is, so this is power counting. So this is a bit too technical to present it here. I can do this pictorially, but we can talk about this later. So we split this into the following dynamical variables. One of them is curly Q, which is really just the velocity. Then there is the rest of Q, that only couples to the density. So their polarization is irrelevant. It's essentially linearized to have, that solves that. And so you plug this here and you see that there's something which is divergence of the Q forces that bit, okay? And so from that you can construct a set of equations where you change the scale and look how various quantities change, and you observe that this becomes mean field at dimension 6.
Okay, so I'll
Not
get
sure I answered this, but
no, I'll get
Okay.
more details later. That's fine. Yeah, thanks.
Further questions?
I wanted to ask about the orbits, the periodic orbits.
Mhm.
So, what do you see and how do you understand it?
so the argument is kind of, really we didn't spend too much time on this because it happens in such a small part of the parameter space that it's largely irrelevant, but the argument is very simple. So if you remember the argument for the mechanism of the active turbulence in the mean field, the first instability is towards a globally aligned pneumatic state. That pneumatic state we know is linearly unstable by itself, so you go from the isotropic to fully aligned, that breaks down. If you have a so that instability of the pneumatic state has a very funny dispersion relation, which is unstable at large scales, but stable above some scale. So if you confine your system small enough, such that that instability does not fit in, what you're going to see is the first kind of instability, and that which is stable. So you go to a pneumatic state, which is more or less homogeneous across the whole domain. It needs to be periodic in order to satisfy the boundary conditions, and so you see this type of profile with 4 vortices and some modification in a density. When you increase the activity slightly, which is exactly the same as, well, you know this, as increasing the system size, there is a first instability of that state. So there is a single mode popping up that becomes time dependent, and this is what periodic orbit means. And then it's very quickly kind of the period doubling gets you out of there into a fully chaotic state.
I guess my question was, what is the mechanism of this oscillation?
I think this is really just the instability of the pneumatic state. That's right. Yeah.
Thanks, Alexander, again.